Hi everyone. Good evening. So I'm Pankaj Kapdi. And today this is our second live session for this week. For this week, and I'll be lecture video of variables. So okay. Am I not? Someone? Hello. Hi. Am I audible now? Hello. Someone please reply. Am I audible? Is my screen visible? You can unmute yourself, right? Okay. So I'll just start with the first problem. Okay. So in this first problem, a function of two variable is given, and you have to check if this function is continuous or not at 0, 0. Okay. So you have two options. So we know that this function is either continuous at 0, 0 or not, and you have to choose the correct answer. So it is either false or true. Okay. So the answer to this problem is it is false. The function is not continuous at 0, 0, and we'll see why it's not continuous at 0, 0. Okay. Okay. So now as we know that if for this function to be continuous, we know that the limit so if function f xy this is continuous, then this, so what will happen first, the limit should exist, limit xy going to 0 comma 0 of this function fxy, the limit must exist. And second thing, let's say this is exist and this limit is equal to L, then we must have that the limit must be equal to the function value at 0 comma 0. Okay, so for the given function, you can see it here, we'll just we just show that the limit does not exist. Okay, now for a function of one variable, we know that if function has a limit, then it must be the limiting value from the left hand side and right hand side must be same. Why? Because the function has only one variable. It's a function of one variable. Okay, so if you want to calculate limit of this function at some point x naught, then you can approach this point either from the left direction or from right direction, right? So for a function of one variable, we say that the limit exists if you approach from right side or you approach from the left side, they both limit should exist and they must be same. But now we have a function of two variables. Okay, so the domain of a function is some subset of the plane R2. Now in the plane R2, if on the plane R2 your variables are x and y, right? Your independent variables are x and y, and you are calculating the limiting value, let's say the limiting value of a function when the point approaches to x naught comma y naught. Now you can approach this point from anywhere, right? If this limit exists, then it should be same when you approach this point from anywhere. Okay, so if we able to show that there exists two paths, okay, in the xy plane, when you approach through those two paths, if it turns out that those limits are different, then the limit should not exist, right? Because if it exists, then it has to be same. So what we'll do, we'll just choose these paths. Now these paths are straight line. Let's say y equal to mx, right? So what is y equal to mx means? Okay, so this is like y equal to x. So these are lines. Okay, so we have to calculate the limit when xy approaches 0 comma 0 origin. Okay, so we will choose paths which passes through 0 0. So we are choosing these paths to be straight lines. So there are lots of straight lines. For example, this is y equal to x. We can have y equal to 2x. Okay, in general, we will choose y equal to mx. So, and we'll show that the limiting value depends on the value of m. That means if you change this value of m, then the limit will change for this given function. Okay. Okay, let's see here. So along path y equal to mx, the limit of this function when you go from approach this origin of fxy, what will it be? Because you put y equal to mx, right? Because we are fixing that y is mx. We are approaching origin from straight lines, through straight lines. So it will be this log of x square plus m square x square under root, right? Plus 3 times x divided by x square plus m square is root minus 3 times x, this thing. So this is limit x square goes to 0 comma 0, right? Now you can see that you can take x square common from this square root, and you can cancel out this x. So this is same as, okay, so what you will get? What is the limit? This limiting value is log of 1 plus m square square root plus 3 divided by 1 plus m square minus 3, right? Now since if if we approach the origin through straight lines of the form y equal to mx, the limiting value depends on the value of m, right? If I choose two different values of m, that means I'm choosing two different paths through different straight lines, and I'm approaching the origin from those two straight lines, and the limiting value turns out to be dependent on m. That means along those two paths, the function limiting value of the function is different. That means the limit of the function at 0 comma 0 does not exist. Okay, so we can say that for this particular problem, limit xy tends to 0 comma 0 of the function fxy is does not exist, right? That is why the function is not continuous at origin. Okay, okay, so is this problem fine? Are there any doubts with this problem? You can tell me, I can discuss it again. Okay, so are you not able to turn on your mic? Because it will be better if you speak up. Okay, let's go to the second problem. Okay, again in the second problem it's a true false question, and here you have to find out if the statement given here is true or false. So what is the statement? The statement says that limiting value of this function of three variables is 0 when you approach to origin, when xyz tends to 0 comma 0 comma 0, that is origin, we'll just write it 0. Okay, so it's a function of three variables, and the statement is that limit of this function is 0 at origin, and the function is given here. This is the function, the definition of the function. Okay, it's the function of three variables. There is a typo, and you have to tell if this statement is false or true. Okay, so you have to find if this limit is actually 0 or not. Okay, let's calculate the limit. It may happen that the limit does not exist, or if this limit exists, then we have to show that the limiting value is 0. Then we have to evaluate it. We have to prove that this limit is 0. Okay, so the answer is false. The statement is false. We'll show that the limit does not exist. Okay, and again the idea is same. We'll choose a path in the, now if this time the domain of the function is not not in a plane. Now we are not in a plane, right? It's a function of three variables. So our domain of the function is a subset of R3, the space. Okay, so we'll just choose a path. Can anyone tell me which path should I choose in R3? So how I'm defining this path? This path, let's say x equal to t, y equal to mt, and z square equal to nt. So this is some curve, some path in R3, and we'll approach our origin through this path, right? Because when t tends to 0, if anyone leaves, our point xyz tends to origin 0, 0, right? Okay, so we let's find out what is the value of xyz along this path. So along this path, what is the value of the function? The function is given to be x y square z square. That means x is equal to t. So now we are writing this as a function of t, right? So t y square, which is nt, right? And then x to the power 4, that means t to the power 4, 2 times y to the power 4, that is 2 times to the power 4, to the power 4. Okay, this is plus, we are adding here, not multiplying, and then minus z to the power 8. So z to the power 8 is, what is z to the power 8? Z square to the power 4, right? And z square is n times t. So this is n to the power 4, t to the power 4. Now notice that in the numerator, we can take t to the power 4 common. So this is t to the power 4 m square n divided by, take t to the power 4 common, 1 plus twice m to the power 4 minus m to the power 4. Okay. So this is the value of the function along this path. Now the limit of this xyz going to 0 origin of xyz along this path is same as, so we are saying that we are approaching this along a path, so we can write that path as gamma. Okay, so we can write gamma here. That is same as finding, taking t tends to 0 of this f of t, right? And because you can cancel t to the power 4, what is this value of the limit? Is m squared times n divided by 1 plus 2m power 4 minus n to the power 4. Now again, we can notice that if we choose certain path, then the value of the limit turns out to be dependent on that path, right? Because now you can take different values of these m comma n, and you can take distinct paths. Let's say you choose two different paths by putting different values of m comma n, and the limiting value of this function along those two distinct paths turn out to be different. Why? Because the limiting value depends on m comma n. When you choose different values of m comma n, you'll get a different limit. So that means that this limit does not exist. The limiting value of this function xyz going to 0, 0, this limit does not exist, right? It means this statement is false. The limit is not equal to 0. It even doesn't exist. Okay.
Sir, it means we have to check on any function and then we have to decide limit exist or not.
Yes. Yes. So limits may not always exist, right? There can be functions which have so there are example in which limit can exist, or there, like in this example, limit does not exist. Okay, so why we are like learning, or we are understanding these limits of the function, because like they will be useful in the when defining continuity, then derivatives, right? The continuity we define in a certain way. We say that the function is continuous at some point when the limit at that particular point exists and it is equal to the functional value. Whatever the value of function takes at that point, we want the limit should be equal to that point, that value. Okay. And then again, when you define differentiability or partial derivatives, then the definition of partial derivative, we also use the concept of this limit. Okay, so that's why the understanding when limit exists and when does not, it is important. Okay, in another problem will prove that the limit exists in that case. Okay, so there are problems where limit can exist. So in this particular problem, these functions were designed in a way that they will not have limit at origin. Okay, at any other point, this function has limits, right? This functions fails to have a limiting value only at origin. If you see, let's take this function first function. Okay, so if you find its limit at any other points, let's say x comma y goes to 1 comma 1 of function fxy, right? Now you can see that the function is defined at 1 comma 1, right? No, the
Yes.
okay, you have to choose a point in the domain. Okay, so what we do, just choose some point in the domain of the function when the so we'll just choose some different value. Let me not write this. So basically, in these cases, we are calculating this limit at origin because the function takes a different value at the origin, right? We don't know what is the behavior of this function at origin. All other points where the function is defined, its value can be the limiting value can be simply find out by putting that particular value. Okay. So
Okay, sir.
let's see the next problem. Okay, this is one problem where you have to find the domain of the discontinuity of this function. So basically, you have to find on the whole set of points where this function is not continuous, right? So what do you do for this particular function? See, first you have to see when the function is defined. For finding the value of discontinuity, the points of discontinuity, first you have to see where the function is defined. What is the domain of the function, right? Like like we know that the function 1 over x, what is the domain of this function? The function of defined is everywhere except at origin. So we write this is domain, right? The function does not define at 0. In a similar way, you have to find first you have to find where this function is on not defined, right? Because this is again a function of type 1 by x, the composite function, right? Instead of x, you have sine of pi x. So you have to see when sine of pi x takes value 0. So if sine of pi x takes value 0, that means it's 1 by 0 form, and that is not defined. Similarly, you have to find when sine of pi y takes value 0. It will be again a 1 by 0 form, and then it will not be defined. The function will not be defined. Okay, so first we have to find that. Okay, so in this case, the correct answer is C. I have written here. Now, when sine pi x is 0, can someone tell me? Sine pi
X
x is
belongs
0.
to n pi.
Can you
Then
repeat
n
once
is
again? When x is
when
equal to
x is equal to n pi.
when x is equal to n times pi.
Yes, sir.
Okay, why you need that n times pi? See, there is a one pi is already there, right? Because we know that sine x is 0. Okay, first let's see when sine x is 0. So sine x 0 if and only if x is equal to n times pi, right?
Yes.
We all know that what is the graph of sine function. So like pi, 2 pi is your 0 origin, then minus pi minus 2 pi, and this graphs, it is like it's an oscillating graph, right? Like this. So all the values of this n pi, basically the multiples of pi, integral multiples of pi, the sign takes value 0, and everywhere it is non-zero. Okay, so n pi, where n belongs to, we have to also see where n belongs to z. So this n can be any integer. So that is n can take value 0, 0, plus minus 1, plus minus 2, plus minus 3, and so on, right? Okay, so now let's see here. When sine of pi x is 0, so sine of pi x 0 if and only if we have seen that the pi x is same as n pi, right? When this pi of x is same as n pi for n belongs to the set of integers,
Yes, sir.
that is equivalent to x is equal to n. Okay, so so our function of two variable is equal to, this function is 1 over sine pi x plus 1 over sine pi y. Okay, now this function is not defined whenever sine pi x becomes 0 or sine pi y becomes 0, right? See, even if only this first term becomes even if only this sine pi x becomes 0, the function is not well defined, right? The first part of the function is not well defined, then it means the whole function is not well defined. So we can say that f is not defined if either x belongs to the set of integers or y belongs to a set of integers, right? So that is the domain of the function. So what is the domain of the function? The domain of this function, this is the, you can take whatever you want from the whole plane R2 except the points. Let's say write m comma n in Z2, not only Z2, except those point xy where either x belongs to z or y belongs to z. So except this set, the function is always well defined, right? Now, so now you know that if some function is continuous, like let's say the function of one variable. So we have these types of result. Let's say gx is continuous. Then if gx is continuous, then 1 over gx is also continuous, except when gx takes value 0. We have, so this is kind of let's say it's a result. Okay, if gx is continuous, then 1 over gx is continuous, except at those points where this gx becomes 0. Right? So what I mean to say that inverse of a continuous function is always continuous except at those values where the function itself becomes 0, right? So now we know that this sine function and sine is continuous, right? So sine of pi x is continuous everywhere. So there is no problem for this function. It is continuous everywhere. That means 1 over sine pi x, this is also continuous, but except at those values where the function takes value 0. So we can say that this function is continuous at or in, right, continuous in the set where x belongs to, or in R minus Z. From the all set, from the set of real number, we will remove all the integers. Then this function is continuous. Okay. Similarly, 1 over sine pi y. Okay, because this sine pi y is also continuous everywhere, and 1 over sine pi y is continuous in, again, the set of real numbers minus integers. You just remove the integers. Okay, now again we have some another result. What this result says, that this says that the sum of two continuous function is continuous. When you add two continuous functions, the resulting function is continuous, right? So it says that, okay, let me write this function from some subset of R2 to R. They are real valued function. They are two function and they are continuous function. If f comma g are continuous in A, then this f plus g, right? How we define this f plus g? F plus g of x comma y is defined as f of xy plus g of xy, right? Because the range or the codomain of these functions are the set of real numbers, and in the set of real number we can always add two real numbers. So that's why we can define this sum of the two functions. Then this sum function is also continuous. Then f plus g is continuous. In A, right? Now just apply this result. Because of this result, now we know that the function of two variable 1 over sin pi x plus 1 over sin pi y, this is also continuous, except in, so this is continuous, but you have to remove the integers, right? Except in this set x comma y in R2, such that either x belongs to z or y belongs to z. Okay, so except this particular subset of R2, this function is continuous everywhere. And this function was not continuous in this particular subset because if you take any point from this set, then either sine of pi x becomes 0 or sine of pi y becomes 0. That means the function is itself is not defined there. Okay, so you can notice that this set as the elements of these sets are of the form, you can write, so one coordinate has to be integer. Okay, so if this coordinate, let's say 2, then we can also put anything, let's say square root 2. One of them has to be integer, then this point belongs to S. 2 comma 1, these kind of points belong to S. If you take any other irrational number e comma 1, these belongs to S. But if any of them, these coordinates are not integer, then they don't belong to S, right? Let's say these kind of values, 1 by half or 1 by 4, this kind of point does not belong to S, right? We want that either x belongs to the integer or y belongs to the integer. Okay, so in this particular case, the correct answer is C. Okay, all those points m comma n where either m belongs to z or n belongs to z. So is this question okay?
Yes, sir.
Okay, so should I move to the next example?
Yes, sir.
Let's move to the next problem. Okay, okay, so this is one of the problem where you have to find out the limit. Okay, so either you have to find out the limit or you can show that the limit does not exist. So what is your opinion in this case? Does this limit exist or it doesn't exist? So if this limit exists, then what is the limit, right? Anyone want to have a guess? Okay. So what we'll do, we will prove that the limit exists and this limit is equal to, the correct answer is A, this limit is equal to 0. Okay. Let me write what is the function. So the function is fxy equal to sine of x square y plus x y square divided by xy. Whenever xy not equal to 0, in the first case we want that xy is non-zero, second way otherwise whatever, because we are dividing by xy, so we want that it is not equal to 0. Okay, so we prove that the limit when xy approaches origin of function fx comma y is equal to 0. This we will prove. Okay, so how do we prove that? So we will use the base the fundamental definition of limit. Okay, so what that definition says, it says that limit of function xy going to 0 comma 0 or some other point, let's say whatever, in general let me write it at x naught comma y naught of the function fxy is equal to L, some number L, if and only if for every real number, whatever real number I take, for every real number, so I write it epsilon, so every real number epsilon positive. So what do I want? This limit this limit exists and is equal to L if and only for every epsilon there is a delta. There exists some delta positive such that the distance of these functional values from the L is always very small whenever this x comma y lies in the some delta neighborhood. Let me write it n delta neighborhood of x naught comma y naught. Okay, so what is the delta neighborhood of a point? So it's just a ball. Take a point x naught comma y naught and draw a circle. Okay, circle of radius delta. So this is radius delta, and all these values which lies in this ball, in this disk, this particular subset of R2 is called a delta neighborhood of point x naught comma y naught. Okay, it's a neighborhood, right? You are taking all those points which lies in at least at most delta distance of x naught comma y naught. Okay, so how we describe this neighborhood and delta of point x naught comma y naught? All set of points from R2 such that the distance, right, distance of these points from x naught comma y naught. So what is the distance from between these 2 points? The distance is given as y minus y naught whole square plus x minus x naught whole square to under root. So we want that this distance is less than delta. And this is your delta neighborhood, right? All those points which are delta distance, like you just take delta distance, all those point delta from this x naught y naught, and collect all these points from a ball or the disk. All those points which are comes in this set, the set is called the delta neighborhood of your point x naught comma y naught. And we are saying that whenever okay, so we want to claim that the function has limit L whenever you approach x naught comma y naught. That means, okay, let understand this concept in function of one variable, and we are saying that this function, let's say, okay, so this is, let's say, your x naught, and this is your limiting value L. Okay, we want to say that function fx, it converge or it tends to L as x goes to x naught. Whenever you come quite close, right? You come arbitrary close as much as you want to x naught, as much as you want to x naught from either direction, either left or right. Okay, the functional value is fx. This should approach this number L. Okay, that means we are saying that however small interval we will take. So this is our epsilon interval. So right, we are saying that the distance between fx and L, the distance is less than epsilon, right? So we are saying that just take some epsilon interval. So this length is epsilon, and we are saying that for every such epsilon, every such interval, this interval, we will have some delta interval here. This delta. So this length is 2 delta. Okay, such that whenever you take values of x from this delta interval, your values of fx lies in this epsilon interval. Okay, note that this epsilon is arbitrary and delta depends on epsilon. Okay, so epsilon we can choose as small as possible. You can choose any epsilon, however small it is. For that particular epsilon, there has to be some delta. Okay, so in this particular problem, we will prove that for a given function. But this is a function of two variables. Okay, so what we'll do, we'll write that take any epsilon positive. For epsilon positive, for any epsilon positive, the functional value of xy from 0, because we want to claim that the limit is equal to 0 when you approach the origin. Okay, so the we'll put 0 at L, and we want to show that this limit, this distance is less than epsilon. Okay, whenever xy lies in some delta neighborhood of origin, we want to show that. Okay, so what is the where what is fxy? It's a sine. Right, sine of x square y plus y x square divided by xy, and we want to approximate this. Okay, now we know that the sine function is modulus of sine is always less than equal to 1. So this is less than equal to x square y plus y x square modulus divided by the modulus of xy, right? Now, what is this equal to? Okay, so we will just assume that xy is non-zero. Product of xy is non-zero. So you can cancel xy by taking common, and you will just remain x plus y mod, right? This is again less than equal to mod x plus mod y. So this is just triangle inequality. Okay, now we can see that this is always less than equal to root 2 times x square plus y square under root. Okay, okay, now we have to make this less than epsilon. So if this is less than epsilon, so when this is less than epsilon, if and only if this value of x square plus y square under root, this is less than epsilon by root 2, right? So what we'll say that choose delta equal to epsilon by root 2. So whenever your delta is epsilon by root 2, the this distance is less than epsilon for all points xy belongs to this delta neighborhood of origin. Okay, this shows that the limit of the function is 0. Limit of xy when xy approach origin is equal to 0. So we have proved that this limit is 0. Okay, so this particular concept is a little bit tricky when if you are seeing it first time, but this is quite common in pure mathematics. Like we always use this epsilon delta definitions to give arguments, these limiting arguments. So if you are seeing it first time, then I can explain it once again.
Can you take one more example of this type?
Okay, so now I have not prepared one more example of this type, but okay, I'll just work out one more for you. What I'll do, I'll just take some function. Okay, so let's take very simple example. Okay, fx equal to, let's say, give any easy function, simple function. Let's say sin x. Fx equal to sin x, and you want to show that the limit of, okay, we want to show that the limit of this function fx when x goes to 0 is equal to, what is the limit? Actually, we can see that the limit is 0, right? Because sine 0 is 0, this is limit 0. But we actually want to prove that. We have to prove that, let's say. So how do we prove? So this is the formal definition, that this limit is equal to 0 if and only if for every real number epsilon positive, there exists some delta positive such that the distance of your function from the limiting value must be less than epsilon for all values of x lying in delta neighborhood of origin. That means whenever your distance of x from 0 is less than delta, your value of the function from 0 must be less than epsilon, and this happens for every value of epsilon positive. Okay, so delta you have to choose depending on epsilon, but epsilon must be arbitrary because we want to go as close to 0 as possible via function f. Okay, that's the meaning of limit. Okay, so what we are saying, that this function, let's say, is our origin, and your function sin x goes like this, right? Okay, so what we are saying that either you go from left direction, approach origin from left, or you approach origin from right. Your functional value, basically the sin x, either from right or left, or okay, so the function also have like this. So the functional values should go in this direction, right? Because the limit of this function sin x is 0 at x equal to 0. Okay, so we have to basically prove that the functional values of f are arbitrarily close to 0. So to prove that, you have to, so what we take arbitrary interval. Okay, so it's a game, you can see it like a game. So if we are saying that this function has limit 0 at origin, that means if you give me some any epsilon, you give me, let's say you give me this interval, take this interval and find out some interval here, so that whenever value of x you choose from this interval, sin x will always lies in this interval. Okay, so you gave me one example, I gave you one delta, you gave me this value epsilon, I gave you this value delta, then you reduce the interval, you can give this smaller interval. So I may give you some smaller value of delta. I can say that instead of this delta, let's take this newer delta prime or whatever. Okay, so it's a game, whenever you give me any epsilon, I will give you a delta, right? Notice that in the previous example, you give me any epsilon, I can give you delta. What is that delta? Delta is epsilon by root 2. You take any real number, give me any positive real number epsilon, I give you delta by just dividing the epsilon by √2. Okay, so that says that we can go as close to origin as we want via the functional values of f. That is the meaning of limit. Okay, so in practice you can prove it like that. Like you have to show that the sin x minus 0, you can make it arbitrary small, epsilon. Okay, by making x arbitrarily less than delta, and this delta should depends on epsilon. For every epsilon greater than 0, there exists a delta positive such that this happens. Okay, and how it is done? For this, one has to use the Taylor series expansion of sin x. Right? You have to write sin x as x minus x cubed by 3 factorial plus x to the power 5 by 5 factorial minus like this. And then you want to approximate this particular series. Okay, so it can be done. Okay, so let's move to the last problem because we don't have much time. I had other problems also, but so in this particular problem, you have to find if you have to choose the correct answer out of these four. So either the am I audible?
Yes, sir.
Okay. So you have to basically choose one of this answer. Okay. If function is continuous at origin, or function is not continuous at origin, or the limit exists at origin or not, or if it exists, what is the limit? So basically, you have to investigate the continuity of this function at origin. Okay. So in this particular problem, the correct answer is that the function is it's continuous. That limit of this function exists at origin, and the function is also continuous at origin. So answer like options A and C are correct. Okay, so we'll see that why this limit exists. Last problem. So this is xy times x square minus y square divided by x square plus y square. Whenever xy not equal to 0, this is 0 at origin. Okay. So how do we find this limit of this function at origin? Any suggestions? See, there is one more way to evaluate limits sometimes. Sometimes changing from Cartesian coordinate to polar coordinates is helpful, right? Because this function is given in polar in Cartesian coordinate, right? X comma y. You can always change a function from the Cartesian coordinate to the polar coordinate, or polar coordinate to the Cartesian coordinate. But sometimes that may not be useful, or sometimes it may be. Okay, so in this particular case, changing this function from the Cartesian coordinate to the polar coordinate, will turn out to be useful. Okay, so first we just let's find what is the function value of this function. What is this function in the polar coordinate? So for polar coordinate, what we will do, put x equal to r cos theta and y equal to r sin theta, right? Then as function of r comma theta, what is this function? Okay, so first note that when this happens, then x square plus y square becomes r square. Okay, because there was this term x square plus y square, therefore it might be useful to convert this function to polar coordinates. Okay, let's write what will happen. This become r square sin theta cos theta in the bracket, but we will have r square cos square theta minus r square sin square theta divided by r square. What is this equal to? You can always cancel this these r square, right? You can cancel this r square with this r square, and you can take these r square common. So we will have r square sin theta cos theta in the bracket cos square theta minus sin square theta. Now can you tell me what is the limit of this function? R theta when r goes to 0, right? Why we are writing r goes to 0? Because you can see that because this x, y, and r satisfy this relation. So if x comma y approaches origin, if and only if r approaches 0, r becomes 0. Okay. So what is the limit? Okay. So what we'll do first, we simplify this function. If this function is looking quite complicated, then we can simplify this function. Okay. So what we will do, we'll just apply this trigonometric identities. Notice that this term is equal to cos 2 theta, right? And this can also be made sine of 2 theta. How? But just multiply by 2 and divide by 2. We'll divide by 2 and multiply by 2. So 2 times sine theta cos theta becomes sine 2 theta, and this particular part becomes cos 2 theta. You can see again we can combine these two functions. Again multiply by 2 divided by 2, then this turns out to 4, and this becomes sine of 4 theta. Okay. Now notice that the modulus of the function, which is always bigger than or equal to 0, is always less than or equal to r square by 4, right? Why? Because sine function is bounded. Sine 4 theta is always less than or equal to 1. Okay. Now can you tell me what is the limit of this function when r goes to 0? Just apply Sandwich theorem. We apply Sandwich theorem. What Sandwich theorem says? It says that if you have a function which is squeezed between two functions, let's say gx or hx. If a function is less than or equal to gx and is bigger than or equal to hx, okay, and if both the functional values x tends to x naught of this gx equal to L, which is equal to limit of x goes to x naught of hx. Okay, if both this function goes to L, this also goes to L when x goes to x naught, then this theorem says that the limit of this function which get squeezed or sandwiched between these two functions, the limit of that particular function as x goes to x naught it also exists and it is equal to n. Okay. Now notice that in our case the function, the modulus of this function lies between 0 and r square by 4. Okay. And this is a 0 function, constant function. Its value is 0 when r goes to 0. And notice that r to the power 4 divided by 4 or r square divided by 4 is goes to 0 as r goes to 0. By Sandwich theorem, your limit of this function is 0. Okay, so that is the this value, this limiting value is 0, because we have calculated this limiting value of this function by just converting from Cartesian coordinate to polar coordinates. Okay, now notice what is the value of function at origin. What is f of 0 comma 0, right? F of 0 comma 0 is equal to 0. Okay, so when the limit of function at a particular point exists and it is equal to the value of that function at that particular point, then we say that the function is continuous at origin, at that particular point. In this particular case, that point is origin. So here we have that the given function, the limit of this given function exists at origin, and the function is also continuous at origin. Okay, because the limit is equal to 0 and the value of the function is also 0 at this point. Okay, so is this problem clear? You
Yes, sir.
okay? Then we'll meet next week with the new set of problems. Thank you all.
Okay, sir. Thank you. Bye.
Okay, bye everyone.